So Chloe will present back to Galaxy, the Andromeda Galaxy, results CO isotopologue and dust emission in GMC of the Andromeda Galaxy. Please go.
Thank you, and let me know if I'm not speaking loud enough. So, hello everyone. I would like to start by thanking the organisers for the opportunity to present my work at this conference today. It's been very interesting so far. My name is Chloe Bosomworth, and I completed my PhD at the University of Hertfordshire in 2025, supervised by Dr. Jan Forbrick. Today, I'm going to present results from my recent paper using a submillimeter array to resolve both dust and CO emission from giant molecular clouds in the Andromeda Galaxy, also known as M31. I hope that by the end of this talk, I will show you that M31 is an ideal laboratory to bridge galactic and extragalactic views of star formation. So first, the motivation. To unify Milky Way and extragalactic studies, we need to study individual GMCs across a range of galactic environments. Though in the Milky Way, we can achieve the highest resolution, this is still difficult due to distance uncertainties and line of sight confusion. On the other hand, in extragalactic observations, GMCs are mostly unresolved. M31, therefore, serves as a bridge because it is nearby enough that we can resolve individual GMCs and substructures, and we can observe clouds across the entire disk. In this talk, I will focus on four main research aims. 1. How do CO and dust compare as molecular gas tracers on 15 parsec scales? 2. Test whether the dust mass to light ratio varies across M31. 3. I will investigate if dense gas structures, which are traced by dust at the sensitivity achieved in this survey, are gravitationally bound and virialized. Finally, I will check if alpha prime CO depends on metallicity by comparing with a survey of an optical spectroscopic survey of H2 regions. We analysed a large SMA survey targeting 80 Herschel-identified giant molecular associations. These are unresolved associations of one or more GMCs. The targets are overlaid here on the Spitzer infrared image, showing we have good coverage of the galaxy disk. The 2-to-1 transitions of 12CO, 13CO, and C18O were observed simultaneously, as well as dust continuum at 230 GHz, meaning they have identical UV coverage, and both are compared on the same spatial scales of 15 parsec. This survey produced the first resolved dust continuum emission detections in individual GMCs outside of the Milky Way and the Magellanic Clouds. Here's an example of a dust continuum image from this survey with CO contours overlaid. 12CO, which is the most extended, is in green. 13CO, which is not as extended as 12CO, is in red, and dust emission, which is the most compact, in blue. I highlight that at the sensitivity achieved, 12CO is tracing entire GMCs, while dust is tracing higher density gas. And I will refer to these dust detections as dust cores in this talk. Across the full survey, we detect 71 dust cores, with 26 being spatially resolved. We calculate dust mass within each dust core using a standard modified black body as shown here, with the parameters as defined in this table. On the right, I show a histogram of the dust masses we obtained for both resolved and unresolved sources. We also extracted CO spectra from within the dust core, so these are being compared for the exact same structures. We fit Gaussian to these to measure the CO luminosity, while the first two papers used CO moment zero maps. This is an improvement because from spectra, we can see which cores have multiple CO sources contributing to the emission, because these show multiple CO peaks in the spectra, suggesting multiple clouds along the line of sight. Since dust has no velocity information, we cannot determine which source is contributing more to the dust emission, and therefore we define a subsample of 46 dust cores with approximately single Gaussian CO line profiles, and this is important for the first result that I will show. But first, before that, I will provide a quick primer. So the CO to dust mass conversion factor, or alpha prime CO, is the ratio of dust mass to CO luminosity. Astronomers will be more familiar with the CO to molecular mass conversion factor, alpha CO, which we get by multiplying alpha prime CO by a gas to dust ratio. CO conversion factors are essential in extragalactic astronomy because the most abundant molecule in the ISM by far is H2. However, it is difficult to observe in the cold ISM. This is where CO comes in, because despite making up a much smaller amount by mass, it is the brightest emitter at millimeter wavelengths. This makes it a primary tracer of molecular gas in extragalactic astronomy. The disadvantage of CO is that it becomes optically thick at high H2 densities and therefore reflects the mass and density of the more diffuse molecular cloud envelope and not the cloud as a whole. This is where simultaneous dust emission is key. Not only does dust make up a higher fraction of the ISM by mass, it is a more accurate tracer of H2 density. However, it is more difficult to detect extragalactically. Therefore, in this study, we are going to constrain CO conversion factors using dust measurements. Here I show the first result, alpha prime of 12 CO for individual dust cores in this survey. We find an average value that is higher than, but consistent within uncertainties with the Milky Way value. And find that alpha 12CO of M31 is approximately constant. So we go from alpha prime CO to alpha CO by assuming a Milky Way standard gas to dust ratio, a correction for helium, and also a CO 1:0 to 2:1 line ratio of 0.7, because this Milky Way value originally calculated for the 1:0 transition has here been converted to the 2:1 transition. We also calculated alpha prime for 13CO. 13CO is not as optically thick as 12CO, and I also highlight that no measurement from a significant sample of GMCs across the disk of the Milky Way exists to compare to this M31 value. And we see that this value is also approximately constant, like alpha prime of 12CO. Now, metallicity. At higher metallicities, more carbon and oxygen is available to form CO. There is also more dust grains, which increases dust shielding, where CO molecules are protected from destruction by UV radiation. Therefore, at lower metallicities, CO is more easily destroyed. There is less CO per H2 molecule. Therefore, theory predicts that alpha CO decreases with metallicity. Metallicity decreases linearly as a function of galactocentric radius in M31, as shown here from M31 H2 regions identified from optical spectroscopy. Thus, one may assume that alpha prime requires a linear correction with galactocentric radius. But what do we see in these results? Because alpha prime depends on both CO and dust, and the relative contributions of their behavior with metallicity is not obvious. And here we test this directly. We cross-match dust cores and H2 regions and find a sample of 30 H2 regions. identified from optical spectroscopy. Across a significant metallicity range, around a factor of 3 in OH, we see no evidence for variation at O over H above 8.5. Why is this? This could be because a significant dependence is expected at lower metallicities, below 8.4. So we possibly see a hint of this with the most left-hand side data point, but a larger sample size is needed to confirm this trend. This could be because at metallicities above 8.5, the effects of metallicity on dust mass and CO luminosity may cancel. Additionally, we do not assume a gas-to-dust ratio in this study, and this is widely speculated to vary with metallicity, and this could be the reason alpha CO varies with metallicity. My final result today will aim to understand the dynamical state of these dust core structures. For this, I performed a virial analysis. Firstly, I want to highlight that Larson's laws imply that GMCs are gravitationally bound and in a dynamical state close to virial equilibrium. For a gravitationally bound system, its gravitational potential energy is stronger than its internal kinetic energy, and this system may collapse to form stars. If the kinetic energy is equal to twice the magnitude of the gravitational potential energy, the cloud is in virial equilibrium. We can estimate the mass of a dust core, assuming virial equilibrium, using this equation, with the parameters defined here. For the velocity dispersion, we get this from 13 CO line widths because it is better spatially matched to dust than 12 CO. We also require an effective radius of the source, which means that we can only compute virial mass for resolved sources. The result is derived by comparing the luminous mass, which is calculated using alpha prime that we measured, and assuming a Milky Way standard gas-to-dust ratio of the dust core with its virial mass. The result shows that 80% of dust cores are gravitationally bound, and I highlight that within 2 sigma, all of these dust cores are bound, and they are close to being in virial equilibrium. In comparison, 12 CO, which traces entire GMCs, are largely unbound from this same survey, while 13 CO clumps are also largely bound. This result provides additional evidence that at the sensitivity achieved in these observations, dust is tracing dense gravitationally bound structures, similar to 13 CO, as well as HCN, which was obtained in NOEMA observations and found to be spatially coincident. This is also in agreement with the physical properties found for clouds in the Milky Way. And there I present my final result, and I'll leave my summary with you, and I'm happy to take any questions.
Thank you, Chloe. Questions for Chloe?
Thank you so much. Very interesting. About the conversion dust to CO or vice versa, CO to dust, if I understood correctly, for M31, you have clouds with both detection of CO and dust, but also clouds with just CO, right? So
yes,
my question
is true.
My question is, the conversion factor that you find based on the detection of both is consistent also for the non-detection in the clouds where you just see CO?
Yeah, this is an excellent question. So I just wanted to show this figure here to highlight that yes, we have CO line profiles from within these structures. Now, from these results, we aim to quantify alpha prime CO of the entire cloud, not just the dust substructures, and we show that these are representative of the clouds, or we indicate this because, for example, two dust cores here located within the same cloud, alpha prime is in agreement within uncertainties. Therefore, yes, we think that the alpha prime values derived here are also applicable to clouds where you do not detect dust, and that's why it's so helpful for extragalactic astronomy, where you largely don't detect dust in observations.
Thanks.
I have related questions. Did you try to compare the flux you recover with the SMA with flux from in 12.0, for instance, for the 30-meter map?
No, but this is a next step that we want to do, is we want to compare with 30-meter data of some of the same clouds and compare the more extended emission with this emission from interferometry.